Hello, my name's Matt, and welcome to an exciting bumper video. It's taking you through lessons 4, 5, and 6 for the Year 6 Coding for Climate Action scheme of work, looking at climate careers and microbits and the different things that microbits do, and just general awesomeness, trying to inspire and get young people into realizing the relationship between coding, microbits, saving the world, being awesome. Why am I so excited as well? It's not just a bumper session. I've got two microbits on me, and that can mean only one thing. We're going to look at radio signals, how these guys can connect to each other and send messages from one microbit to another microbit. So, what am I nattering away for? Let's get into it. Scroll down, you know how to get here. If you don't, yeah, I mean, you can see like the website URL there, and it's really clear. Scroll down. And you've probably got the resources already, so you probably don't even need this. Click on Year 6 if you don't know. That brings you to the free resources and materials for this unit of work. Yes, I'm going to need the work journal. Yes, I'm going to need the career skills chart as well. And yes, I'm going to need lesson 4. So you can see there's loads of stuff here for lesson 4. There's lots of peripheral materials, all of which we'll look at in due course. The reason why we are looking at lessons 4, 5, and 6 all in one go is because the first half of lesson 4 is looking at how we can use radio signals to upgrade some of our kind of existing programs. So we have distributed functionality, right? We don't just have a microbit responding there and then. This microbit is in an earthquake or in a landslide, and this microbit is warning us. Instead, we can have it distributed. So we've got a sender and a receiver. We've got one microbit experiencing the phenomena and sending a warning to another microbit, and this other microbit is the one that doesn't shake. This one shakes, and this one gives us a warning. Okay, so we're distributing geographically our system, and that makes a bit more sense, doesn't it? Let's be honest. If we're in a landslide ourselves, we probably know about it already. So the first half of lesson 4 is looking at that, and then the second half of lesson 4 and the rest of the lessons 5 and 6 are an independent project where students can work together or in groups. Is that an independent project to be in group? I'll let you worry about that. Where students can work to create their own environmental, climate-related warning system or device. Okay, so we're taking together all of this learning and thinking that we've been doing and coming up with our own projects. So let's have a look. We've seen the lesson plans. We know there's loads of support in there and all the links that you need. Hopefully that makes sense, the learning objectives and things like that. So please don't think me miserly for not going in there. So radio signals, we're going to understand how radio signals allow microbits to communicate. And I've kind of talked already really about why that's important, why that makes sense. So I'll gloss over it if it comes up again. But of course, we need students to understand that we can have microbits communicate. They can connect to one another over radio waves, right? And okay, and I'll show you the code for that, or some code for that right now. So the first thing is we want students to predict what these two bits of code do. So we've got microbit 1 over here and microbit 2 over here. If we make this a bit bigger so we can see it maybe. So on microbit 1, we set the radio group to 1. I'll talk more about that in a second, and show a heart icon. And then we'll recognize this code, right? If temperature is greater than 20, send a number 1, okay? These are unrelated. That's probably a bit of a nuisance having them both as 1. But we set group to 1, and then if at any point the temperature goes over 20 degrees, we send over radio the number 1. So out into the anywhere, that number 1 goes. Microbit 2 is also set to radio group 1. And what that means is that it can communicate with any other microbits on the same group. Okay, so because they're both on group 1, if one of them sends a message out, the other one can receive it. But if one was on group 1 and the other one was on group like 17, they wouldn't, even though they might be sending or programmed to receive things, they wouldn't, because they're on different channels, different groups. a bit like an old-fashioned walkie-talkies, where you change the channel on your walkie-talkie. Okay, so I've got 5 walkie-talkies, and one of them's on group 2, and the rest of them are on group 5. The one on group 2 can't communicate with the others, even though it's like could. Okay, so that's exactly the same principle here, and that's going to be important when everyone is in the class is making their own projects later on, or in fact doing these activities later on. Anyway, so microbit 2, we set it to radio group 1, so it can communicate with microbit 1. Fantastic. And then whenever it receives a number, doesn't matter what that number is, 1, 100, 2000, doesn't matter. Whenever it receives a number, it will then do the following code. Oh, that's why it's radio number 1. I wrote this code. You'd think I'd remember. If the received number is 1, then we're going to set off an alarm system. So we're going to repeat this 4 times, show an icon, clear the screen, set an alarm off, and then pause. And those 4 things will happen 4 times and then stop. Okay, and if microbit 1 senses the temperature's over 20 again, it will send a number 1 again. So microbit 2 will respond again. So hopefully that makes sense. We've got some kind of prompting sentences for students to do there. And of course, we've got the task in the work journal for the students to complete as well. Okay, so there we go. That's it explained on the next slide for you to work through with students. And of course, we're trying to draw out some of the programming fundamentals as well. So where is the loop? We've got that and the repeat 4 times, but we also have a forever loop there. So it's got 2 different types of loops. And both of the microbits have got an if statement as well. Okay, temperature being bigger than 20 triggers sending the number. And if number 1, if that is true, that triggers the alarm to go off on the other microbit. Cool. So a bit of reflection on what this could be for, because of course we want to actually relate this back to kind of climate crisis. So, but we're also broadening our thinking that we've got these sensing systems, and they could be for anything. So it could be, and that can bleed into or think about the climate crisis and how we can address that. So it could be used to, rather than being a warning sound, it could be actually that could represent automating a cooling system to save energy. It could alert for wildfires. It could help urban planning. Okay, so we can think about placing microbits and keeping track of how many times the alarms go off or things like that, or measuring heat levels to help us guide building placements and so on. Okay, so loads of ideas about, hopefully it's enough ideas to help students think bigger about what these kind of things are useful for. Okay, so what you might have noticed as well is that if microbit 2 receives number 1 and sets an alarm off, actually we could use that in multiple scenarios. And if we could just amend microbit 1's code, we can have the receiver triggered by different things. Okay, so how can we change microbit 1's code so that when it shakes, it will set the trigger off on microbit 2, or we press a pin, it triggers microbit 2, or the light level goes over a certain level, it could trigger the alarm going off as well. Okay, so we want to modify the code to do that. And if we actually have a look over at the work journal, you will see there we go. It's an area to put the screenshot of the completed code and what type of natural disaster that could be used to warn against. Okay, and if students are uncertain how to do that, first of all, we've got some completed code for you to use. Okay, so that's for you to use as the teacher, also to show students. But can we get students to look back at the previous lessons where this exact code has been used? Okay, so in lesson 2, and in your work journal, the student's work journal, there are examples of how that code is used as well. So can students start now? Hopefully you can see we're trying to encourage students to start thinking independently about code they've already experienced and how it triggers or doesn't trigger certain alarms going off, and think about how they can start designing and utilizing their own code. Having done that, you might not have much of the lesson left, but we want to move students on if possible to the task for the next couple of lessons after this as well, which is to design a microbit climate device. So in pairs or individuals, it's up to you as a teacher. We want students to design, code, and present their own climate-focused microbit device. So the project needs to include a company name, okay, what they're going to call themselves, as well as device name. So what is the device's name? What is it going to do? So Climate Hero Company and the wildfire, what it brings to you, the Wildfire Watcher, for example. Whether your device responds to or prevents a climate crisis. So is it an early warning system? Or is it something that actually monitors energy and reduces climate energy consumption, that sort of stuff? So what is it trying to do? Is it trying to stop bad things from happening? Or is it trying to prevent the climate crisis in the first place? A design worksheet, which we'll have a look at in a second, a sketch of how the device works, which will be useful because some groups might not get their coding done. They might get a bit stuck, but that's okay, right? That happens. If you've sketched out how your device works and where it would go in the real world, that really helps you as a teacher know what the ambitions were of the project and what the kind of the vision would be if they could get it working. And fingers crossed, a microbit programming that actually runs on the device. So to help show students what you need from them, here's first of all the design sheet, and you might have spotted that from over here. So you can share this with students, print it out, or share it electronically. And in this sheet, students can complete it or fill out name of the company, name of product, the problem they'll solve, what the inputs to the program will be. What did it say for I'm sensing the input will be like the temperature going over a certain amount, or will I use Create AI, or will I use radio channel? So wherever possible, fill out this whole worksheet to help break down the problem into different parts and help students know what the inputs will be, what the outputs will be, some of what the processes will be. Okay, and there's a completed one here that you can use to support students as well. So this one is Earth Tech Energy Watch, and the problem is solving is monitoring heat levels and sending a warning to say when a building's heating should be turned on or off. So we'll be detecting heat levels, temperature, and we're going to log the temperature. Which microbit sensors or creates AI? So we're going to use a temperature sensor. What questions do we ask? We want to check if the temperature is over or under 10 degrees. It's under 10 degrees, we need the heating on. Over 10 degrees, we need the heating off. We're going to use a radio channel, channel 100, and we're going to send the numbers 1 and 2. 1 would mean turn the heating on, 2 would say the heating off, for example. And then we can see the output from the device is going to be a warning symbol and sound for too hot and too cold. And we can see how the 1 and the 2 is going to help. Hopefully you can see how that's going to help develop that. Hopefully that makes sense. And a point here really is that students really need to have to be using different channels, and that's in the learning guide as well. They all use the same channel, then all our microbits are going to be like communicating with each other, and that shouldn't be the case. I don't want my microbits, my warning system, triggering somebody else's warning system doing. Cool. I could have just shown you here, couldn't I? Never mind. There we go. And then once the design sheet is done, we can have the example model done. So what it will look like in the real world, annotating it with input, sensors, and output. So more of the same, but just seeing in a real world scenario as well. And at that point, we can stop and share. There might be, we might want to have students compare their notes, compare with one another what they've done, support one another. How's the idea evolved, so on and so forth. So it's good to stop and share. And then once students are ready, because students will be working at different paces, right? Or groups will be at different paces. Once students are ready, they can work on the actual build themselves. Okay, now I wouldn't imagine that this will be happening in lesson 4, but some students might just rock through this and get really far. So if students are ready in year 4 in lesson 4, this lesson, to complete their build, yep, fantastic, you can go for it. They can either just go and do the microbit programming by themselves, looking back at previous work, no problem. But it might be that some want some support code as well. Okay, so we can see in the folder, we've got loads of support code. So of course, please do share this with students, put it on the screen, print it off, share it with them. So we've got lots of examples of existing code that they've already used throughout the lessons to help them build and develop their own code So I won't go through that in fine detail, but lots of different ways you can use the different sensors and things like that on the microbit in the scenarios we've looked at so far, whether it's using one microbit or radios, is all covered in there. Now, the one thing to think about is how students are going to carry their code forward from one lesson to another. In the learning plan, there is a guide on multiple kind of methods of doing that. So you can decide yourself how you want that to happen. So we've got, if we have a look here, there's some details here about saving microbit projects. What we have suggested is, if I just open up a random microbit project here, heat detector. So let's say the students have gone to microbit, they've started their program, they're working on it, they're halfway through it. This is not complete yet, but they want to save it for, it's the end of lesson 4, we need to save it for lesson 5. You can click on this share button here, and then click on share project, give it a name, share project, and that will create a link. Now, if I copy that link, you will see we have put a spot in the work journal at the end of lesson 4 here. So I'm just going to copy and paste my link in there. So now when I come back for lesson 5, I can use this link, and we will see that when I use that link, it takes me back to the code that I had at that time. So I can pick up my code, go to edit code, carry on working it. At the end of lesson 5, I can then share it again and put it in the work journal at the end of lesson 5. There we go. There's my share link ready for the end of lesson 6, should that be needed then. Hopefully that bit makes sense. End of lesson 4, please do complete the career skills log. So we've been through that a few times. So I'll do mine today. I have programming. I did like a 1, I think, because I didn't do lots of programming. Teamwork. I had to do some good teamwork because I was using the radio signals, and the radio signals felt like engineering to me as well. Okay, so there we go. That's my score for here. Still mostly programming. Teamwork is bulging out a little bit, but still I'd say programming and technology and design are kind of my key areas of skills at the moment. Okay, cool. Let's oh, and you can see hopefully on here how the lessons we can see the incremental change for each lesson. Yeah, so it's kind of storing your skills are getting bigger and bigger and bigger, but it's showing your record for each level. I'm really quite proud of that radar chart. That's such a nerd. Okay, so that's lesson 4. If we have a quick look at lesson 5, you will see that, let's get rid of this stuff that's in the way. You will see that a lot of it is the same. So we'll need the worksheets, the design worksheets from the previous lesson. You'll need your code from the previous lesson as well. But we can see as well that we're just reminding the students about their climate program. We're reminding students about the design aspect here, reminding them about the build, reminding them about the support cards. And once students have got through and feel like so that I'd imagine would take a lot of lesson 5, working on this, testing it, get it working, and so on. Once students have got quite far with their project, we then want them to test their microbit. Does it do what they think it should do? And testing is a really vital part of developing any computational system, because if you don't test something, then you can't spot any errors. It might not work as expected, and things can go, in some cases, catastrophically wrong. That's not the case with our microbits, but we still want to test. So the testing should ask students to identify 3 different inputs they want to test. So shaking the microbit, for example, this is mine. I'm going to have it like different shakes and lots of shaking, or just one shake and things like that. So that's the planned test I'm going to do. And what I think will happen. So my test 1 is shake the microbit gently. Should blank do nothing, because it should only do something over 3G, for example. So, and if it passes the test, we put in passed. If it doesn't pass the test, then we put in failed, and talk about what we need to change, what we need to check. If we can fix it, we want to fix it. Where do students do this? It is in their log here. So there we go. So we put all of the tests and descriptions in there. Cool. And once tests are done and the whole class is, got to a point where they are ready to finish their project, then we'll have our presentations. So you can see here, we want students to include these in their presentation: the company name, the solution, what are they trying to do, what techniques, what programming techniques have they done, have they used, what testing did they do, what were the challenges, and were the students able to overcome those challenges, and general reflections on what they would improve if they did that again. Now, if you like, while students are doing that, you can use this rubric here to sort of as an assessment tool. So students can you can say whether students have met these assessments or not. Yeah, so you can kind of think about how well they've progressed against the rubric and the overall learning of the unit of work, and use it to prompt any questions and things like that. Finally, once all of that is done, a final career skills update. So there would have been one for lesson 5. So I did loads of programming and loads of teamwork. Those are mine because that's what we did together. And the same one here. And actually, maybe I tried to make a circuit, so a bit of engineering and teamwork. Okay, so there we go. That's my final career skills. So where have I maxed out at? Mostly programming. Oh, interestingly, I've kind of edged out the teamwork as being the other thing. So I'm a team player and I'm a programmer, but you can see I've got loads of skills in other areas as well. So having completed that final chart, we want students to reflect on the skills they have developed and what those skills mean. So we've got in the work journal, the final activity, think about what is your top skill and use that to find out what sorts of careers you could have in the future. So here we go, here it is. So mine was programming. So the careers I could have as a programmer: general career, game developer, awesome, or climate career, environmental data coder, write code to help scientists study climate data and find ways to protect the planet. I'm going to choose that one. If I was 11, I might not choose that, but as a 42-year-old man, I'm choosing the climate career. My other option was teamwork, wasn't it? General career, robotics team member. That's pretty cool. Worked with us to build and program robots for competitions. Nice. Or green technology project leader. Leads a team to create tech that helps reduce waste and save energy. Nice. Ah, okay. My career choice would be, in this case, I think climate careers, green technology leader, because I like working with other people and I like to do things that are for good. So that would be my rationale in there. And there's an exemplar answer as well you can look at. So then that would be the unit wrapped up. The very final thing to just remind you of and beg is, if you're seeing this slide 15 in the unit of work post survey, please do take just a moment to fill out the survey. It really helps us feedback to our other partners how well the unit of work has worked, and think about how we can improve, and obviously look to find ways that we can carry on doing more stuff like this. Thanks so much for this, and at any point, just get in touch with the charity, info@digital.charity, if you would like to ask us any questions or need more support. Thanks so much. Bye-bye.